I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts! Great Scott! What the hell is a gigawatt?
What is a kilowatt and what is a kilowatt hour? These two units of measure are often used interchangeably, but they're actually quite different. And one of them, kilowatt, is a metric measure for power. Kilowatt hour is a metric measure for energy. Now, if you pay the utility bills at home, specifically the electric bill, you're probably familiar with kilowatt hours. The utility company uses that to gauge or to measure the amount of electrical energy you've used in a given period of time. But a kilowatt hour doesn't need to be used just for electrical energy. It's a measure of energy. There's different forms of energy in the universe. Well, there's two categories, kinetic and potential energy, but I'm not going to go that deep into it. We can use this to measure other forms of energy. And specifically with home heating, we might want to use that to relate to fossil fuel systems. More and more today, homeowners are looking at electrified systems for their heating systems, and heat pumps in specific. And when you try to compare the consumption of electricity of a heat pump to the consumption of a fossil fuel, the two don't really relate, because a natural gas furnace is rated, consumption is rated in cubic meters of natural gas. Propane furnace would be liters of propane, and an oil furnace would be liters of oil. So how do you get them on the same playing field? Well, it's very easy. We just have to rate them all in kilowatt hours. So first of all, let's get started with a little bit of a definition here of a kilowatt. Let's break it down to brass tacks. A kilowatt is 1,000 watts, and a watt, again, is a measure of power. And a power is essentially how fast something is generating or using energy. Now, energy can't be generated from nothing, so generating could be better termed as converting from one form to another, i.e. natural gas. We burn the fuel, we burn the natural gas to get heat energy out of it. So power is more how fast something is converting energy. It's a rate of energy transfer that would be equal to, in the case of a kilowatt, 1,000 watts. And so the watt is named after a Scottish inventor, James Watt, 1736 to 1819. And he was most known for the development of the concept of horsepower, but also was arguably most responsible for the Industrial Revolution alongside Thomas Newcomen. Now, Thomas Newcomen had invented the steam engine. James Watt optimized it and made it more efficient, so that arguably it was more useful for the Industrial Revolution. But that is a whole other video. So a watt is used to quantify the rate of energy transfer, and it doesn't have to be just a measure of electrical energy transfer. We could talk about thermal energy transfer, and that's what we're going to talk about in today's video. So with fossil fuel systems like natural gas, propane, or oil, the energy conversion is done through combustion. You know, we don't just pour the fuel into the furnace in the basement and expect to get heat off of that. We actually have to light it up with a match, so we combust it. Well, not a match. We actually use a little igniter in the furnace that shoots an electric charge into a gas chamber where it explodes, and then we get heat out. We bring in a controlled explosion into your house to heat your house with fossil fuels. That is what we do. And there's some byproducts off of that combustion process, like carbon dioxide, carbon monoxide, sulfur dioxide, water, nitrous oxide. Along with that goes heat, because no combustion process is 100% efficient. It's impossible. Those byproducts, along with heat, we vent out into the atmosphere. And so we're left with a quantity of heat that we distribute through either a forced air ductwork system in our house, a radiant floor system, or a radiator system. Or we could use it in a water heater and heat our domestic hot water. So we want to be able to quantify the amount of energy delivered to the home. And typically in the industry, we use BTUs, British thermal units, to quantify that amount of energy. But that could be converted to a metric form, which we're talking all metric today. So BTUs can be converted to kilowatt hours as well. It's important before we go further here to note that the energy content of each fuel per unit measure, whether it be a cubic meter of natural gas or a liter of propane or a liter of oil, it varies based on the fuel. So a cubic meter of natural gas has a different energy content than a liter of propane, than a liter of oil. So if you combust natural gas, you'll have a different amount of BTUs than you would of combusting a liter of propane, right? So and that energy content is typically measured, again, either in BTUs, which is a British thermal unit. And a British thermal unit can be defined as the amount of energy it takes to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And again, more commonly, that's in Canada metric system, we can convert that to kilowatt hours. 1 kilowatt hour is essentially 3,412 BTUs. Now, a kilowatt hour doesn't mean kilowatts you're using per hour. It is simply a unit of measurement that equals the amount of energy you would use if you kept a 1,000 watt or a 1 kilowatt appliance running for an hour. So it's the amount of energy that you would use. Now, with a renewable thermal system like geothermal, we use the heat energy stored in the earth as a source for heating. So the thermal energy is already there. We don't have to burn or combust anything to get it. We just need to be able to transfer it from its current position in the earth into the home. And so that's what we use, a heat pump and a ground loop heat exchanger to help us do that. Now, we use electrical energy to power the heat pump because it is a heat pump is essentially a refrigerator. So we have to power that refrigeration process and the small circulators that circulate the fluid around the pipe, the ground loop heat exchanger that's in the earth to pick up that thermal energy. But we have great benefit from doing that. So the work we put into, or the electrical energy that we put into the system is far less than the thermal energy that we get out of the system. So the work energy we put into it must be less than the energy that we get out of it. Otherwise, there's no point in doing it. We would just hook up an electric heater to heat our house. An electric heater is 100% efficient. We plug it in, we get 1 unit of energy from the grid. That equates to 1 unit of thermal energy of heat. So it's 1 for 1, 100%. So if we're going to go through all this trouble of a heat pump and a ground loop, we're gonna want a heck of a lot more than 100% efficiency from our system, which we can get. We can quantify the thermal energy we get from the ground at any ground source heat pump by just measuring the temperature difference between the water coming in and the water going back out to the ground. There will be a noticeable temperature difference there. And we can measure that to understand how much thermal energy we're actually extracting into the heat pump. So by knowing this, we can determine the performance of the system. And the performance of a heat pump is measured in COP, which is coefficient of performance. And typically this coefficient of performance falls in the range of 3.5 to 5. So that essentially means 350 to 500% efficiency. So for every unit of energy, electrical energy, or every kilowatt hour that I use to power the system, I get 3.5 to 5 kilowatt hours worth of heat into the home. So 350 to 500% efficient. So that also means that anywhere from 2.5 to 4 times the amount of electrical energy the ground is actually providing. So 1 kilowatt in from the grid, 2.5 to 4 kilowatts from the ground. Total equals 3.5 to 5 into the house. So that 2.5 to 4 kilowatts is actually free thermal energy. Now, if you then consider the efficiency of the fuel burning process in any combustion system, and reminding ourselves that any combustion process cannot be 100% efficient, as there will be losses, now we start to see how the cost of running a ground source heat pump as compared to a fossil fuel system can actually be very low, even in relatively high electricity price environments. The savings are also amplified when you compare this to systems like oil and propane furnaces, which are essentially delivered fuels that don't use a massive pipe network right to your home to get the fuel there. It's more expensive to deliver these fuels on the backs of trucks to your home. And then also specifically with oil furnaces, they do not burn near the efficiency of natural gas or propane systems, which can use condensing technology. So most oil furnaces burn in the efficiency range of 80 to 85% rated efficiency. And so the price that you would pay to heat your home with oil is that much higher because also the fuel cost is that much higher. So to give an example, I've had an energy analysis done on my own home. We talked last week in my last video about the energy audit process. So I've had that done in my home. So I have a real understanding of the amount of energy my home needs for heating and cooling throughout the course of an entire year. Now, this isn't fuel specific. This is the energy load of the building. So the building situated, I live in Wellesley, Ontario, and my house is, 1,800 square feet. And based on the performance of the building, we can understand how much energy we need for heating and how much we need for cooling. And so I've equated that out to 33,700 kilowatt hours a year of energy. That's not electrical energy, that's energy, thermal energy that we need for heating and cooling. And so with a ground loop with a geothermal heat pump that connected to a ground loop, the electrical energy I'd actually have to buy from the electrical grid to provide 33,700 kilowatt hours worth of thermal energy to the home, so to meet the needs of the home, is actually only about 8,800 kilowatt hours. The rest of the energy is coming from the ground loop, right? That's that free thermal energy that we're extracting from the ground. So this equates to a COP of 3.8, so that's 380% efficient, so well within that range that we had talked about. So again, I'm only paying the electric utility 8,800 kilowatt hours of usage. And so let's say we're using that at 16 cents a kilowatt hour. I mean, that's the peak time of use rate, I think, around here right now, and that varies. And actually, studies have been done to show that ground source heat pumps, my heating system is going to operate most off in mid-peak. So I'm being conservative here. That's about $1,400 per year. Now, let's say my house was on propane. And I have to look at the numbers here. So if we convert this house to propane usage, I can model that out to understand how much propane I would have to use for heating. That would turn out to about 4,800 liters per year. And if I multiply that out by, convert that to kilowatt hours, that essentially equals 33,984 kilowatt hours. So there's that comparative there. That's the amount of energy that we're delivering into the home. And let's say we're at 65 cents a liter of propane, which I don't think is out of the realm. We'd be about $3,325 a year just for heating. And then we'd add cooling to that because my original figure had cooling. So depending on what type of air conditioner I have, I could be a few $100s a year just for cooling. So quickly we get to a savings of about $2,000 a year compared to propane. Oil would be probably fairly similar, $2,000 or a little bit more. So you can see how that $2,000 a year can start to add up quickly to the cost of a geothermal system. So I hope this was educational. It's confusing looking at different metrics of quantities of fuel, kilowatt hours, electrical energy, and then understanding the energy alone that you're getting from a ground loop for free. Because again, and this is an important point, we are plugging into the grid to move the energy from the ground. We're not generating the energy from the grid. That energy is already generated at the power station, and that's powering our heat pump to move the thermal energy from the ground loop into the home. So that thermal energy is free. We're just extracting it with the heat pump, and that's renewable. That will always be there for our home for 100 years. So I hope this was helpful. If you have any questions on geothermal systems or what it might look like for your house, I'd be happy to chat with you. Just give us a call give us an email at hello@evolvethermal.com, Evolve Thermal Energy. We're here to help homeowners retrofit to an electrified future. Thanks very much.